In this video, we will model a simple pump house layout in AutoCAD Plant 3D, including pumps, manifolds, piping components, and maintenance access. First, we need to model a containment pit where the pumps will be located. This concrete structure helps contain possible leaks and collect drainage from the equipment. In this example, I will create a 6 by 4 meter square pit. To model the pit, I will create two solids and then subtract one from the other to form the inner space. Next, I add 4 lines that will serve as our axes. Later, it will be easier to measure distances from these lines. I place them along the inner edges of the pit. I place these axes at the 0 point of the model. This means that the floor of the pit will be located at elevation 0. Next, I add the imaginary pump house manifolds, the suction and discharge lines. For now, these are just 2 large pipes crossing the pump house. The suction line runs at the lower level, and the discharge line is positioned above it. I place 3 identical pumps. These are fairly large units, each approximately 1.5 meters long. First pump I place on the axis and move it away by 1.5 meters. The other 2 pumps are placed with the same spacing. My idea is to use pumps with DN250 suction and DN200 discharge nozzles. Since I have 3 pumps, I need to recalculate the manifold sizes. I sum the cross-sectional areas of the 3 branch pipes, and then convert that total area back into an equivalent manifold diameter. This gives me approximately DN450 for the suction manifold and DN350 for the discharge manifold. If we keep the manifolds the same size as the pump nozzles, the fluid velocity inside the manifold will increase when multiple pumps operate at the same time. Higher velocity leads to higher hydraulic resistance and additional pressure losses in the system. Recommended fluid velocities for pipelines can easily be found in engineering guidelines and on the internet. For example, in water pumping systems, the typical recommended velocity in pump piping is usually around 1.5 to 3 meters per second. I select the pump nozzle diameter one size smaller than the pipe. This is often done because pump manufacturers usually define standard nozzle sizes that are slightly smaller than the connected piping. The pipe is then expanded using a reducer to maintain lower fluid velocity and reduce hydraulic losses. At this stage, I adjust the manifold elevation to align properly with the pump nozzles. In other situations, when the manifolds already exist, the pump house elevation is adjusted to match the manifolds. Here I add eccentric reducers on the suction side. They are used to avoid air traps in the pipeline. A concentric reducer would create a small pocket at the top of the pipe where air could accumulate, so eccentric reducers are typically used in pump section piping. Now I connect the discharge lines. At first, I thought about adding a bend at the top to help reduce stress on the pump nozzle. The idea was to place a pipe support near the elbow so the load would not be transferred directly to the pump. However, it became difficult to connect this arrangement cleanly to the manifold, so I decided to keep the line without the elbow. In this case, the pipe can still be supported, just at a slightly longer distance from the pump. When designing pump piping, it is important to consider the stress acting on the pump nozzles. If the pipes are too rigid or unsupported, their weight, thermal expansion, and hydraulic forces can transfer loads directly to the pump casing. Excessive nozzle loads can lead to misalignment, vibrations, or even damage to the pump. That is why piping near pumps is usually designed with supports, and sometimes with additional bends to reduce the stress on the nozzles. Now that the pipelines are in place, we can start adding some components. First, I install valves to isolate the manifolds from the pumps for maintenance purposes. For this, I selected widely used butterfly valves. When placing the valves, you also need to check that the valve disc has enough space to open. It should not collide with nearby components, for example the disc of a check valve or other internal parts. let's make a few small adjustments so the valve looks cleaner in the model. For example, I will remove the long lever and simplify some of the visual details. Since we do not have real parts for this model, we can take them from the AutoCAD library. If you have a real valve model from the manufacturer, you should always check its length and adjust it accordingly. I measure the distance from the floor and notice that the discharge valves are quite high. This means they will require maintenance platforms. In general, if a valve is installed higher than about 1.8 meters, a platform is usually needed to safely reach it. We will design the maintenance platform later. For now, let's return to the piping and add the check valve. The purpose of a check valve is to allow the fluid to flow in only one direction and prevent backflow. This is especially important in pump systems because when a pump stops, the fluid could otherwise flow back and potentially damage the pump or rotate it in the opposite direction. Now I add saddle connections for the pressure gauges. A saddle connection is a small fitting attached to the surface of a larger pipe. It creates a branch outlet that can be used for instruments like pressure gauges. This solution is commonly used when only a small connection is required, and installing a full T would be unnecessary. These connections allow us to measure the pressure inside the pipeline during operation. Pressure gauges are very important in pump systems because they help operators monitor the pump performance and detect possible problems such as blockages, cavitation, or abnormal pressure conditions. Another very important component is the strainer. It is used to protect the pump by filtering out debris from the fluid. I also use the strainer connection as a drainage point for the pipeline. I will slightly modify the strainer geometry because the default model generated by the program is unrealistically large for this layout. Do not forget to orient the strainer bucket toward the correct side. I have heard cases where strainers were installed backwards because the correct orientation was badly indicated in the drawings. These large diameter strainers do not fit inside our pump house, so I need to adjust the size of the concrete pit. It is always easier to fix these issues on the drawing rather than later on the construction site. To solve this, we will raise the manifolds and extend the concrete pit. The pumps also need to be raised from the floor because we need space for the piping components below. For this installation, I choose a concrete foundation for the pump unit. In other situations, metal frames can also be used. To keep things simple, I model the foundations as solid boxes without spending too much time on detailed geometry. Here I make the foundation edges 10 centimeters wider than the pump frame to allow space for the anchor bolts. Now I quickly adjust the pipelines to the new positions and copy the components to the other pumps. Next, I add manometers to monitor the pump operation. I do the same on the discharge line, so we can compare the pressure difference between the suction and discharge sides. Inline instruments are often installed using smaller connection pipes. A DN15 pipe with threaded ends is very commonly used for instruments such as pressure gauges. In some cases, when the instrument is larger or requires a higher flow capacity, a DN25 connection may be more suitable. Saddles are commonly used for instrument connections because they provide a more rigid and stable installation. If a small pipe is welded directly to a large pipe, the connection can be relatively weak. A saddle spreads the load over a larger surface of the pipe, making the branch connection stronger and more reliable. Let's extend the pit one more time to make sure all the large pipes fit inside. Now let's add pipe supports. In this case, I place one near the manometer connection. In some situations, especially with large diameter pipes, supports are installed close to instrument connections because they provide a convenient structural location. When designing pump piping, supports should be placed close to the pump nozzles. This helps carry the pipe weight and prevents stress from being transferred to the pump. As we can see here, the manifold support interferes with another pipe. This highlights the importance of properly adjusting the support leg lengths to avoid clashes in the layout. Now I quickly create a metal frame for the pipe supports to rest on. I keep it simple, just a rectangular shape. I align the supports in one row so that a single metal frame can support all of them. Now let's quickly create frames for the manifold pipes. I simply divide the existing frame into smaller sections. Our pipeline layout is complete. Now let's create the pump house columns, just for visualization. Now I add a door in the middle of the front wall. I use a standard door size, approximately 1 meter wide and 2 meters high. The edges of the pit are raised about 700 millimeters, so we will need stairs to access it. I noticed that the stairs should be placed a bit further away from the door. Otherwise, it would be uncomfortable to open the door while standing on the top step. Inside the pump house, we will also need a step. I insert a worker model to check whether the valves can be easily reached. The person model I use is about 1.8 meters tall. Using a 3D worker model is useful not only for checking height reach, but also for verifying whether a person can reach components that are further away, for example across a fence or barrier. Here I quickly create a maintenance platform for the valves located on the discharge lines. Actually, I am not very satisfied with the solution, because the operator would have to bend under the pipes to reach the inner valve. However, in this situation I could not find a better solution. The platform is designed with steel grating, and stairs are added to provide safe access. In the end, I add railings along all the platform edges for safety. And that completes our pump house model. In this example, we created the piping layout, added the main components, supports, and maintenance access. Even a simple model like this helps identify many practical design issues early in the process.